Well, I'm not going to talk to here about the fundamental theorem of calculus or any theorems about definite integral. All I want to do is just explain to you what definite integrals are visually, and also to compare them to indefinite integrals, which we were doing a lot of in the previous videos. So let me just write out the indefinite integral and then we'll compare. Okay, there we are. So when you were doing indefinite integrals, if you remember, you had a constant of integration. There were a number of videos on how to find the constant of integration and why that constant of integration needed to be there. Now, in the definite integrals, you no longer have the constant of integration because there are lower limit and an upper limit for the integration, and therefore the result that you get has a numerical answer. It no longer has some constant attached to it, it actually has a numerical answer. So when calculating definite integrals, we can omit the constant of integration c, as this is always going to cancel out in the subtraction process. But when working with definite integrals, we are going to need to define an interval. For instance, let's draw a continuous function on a coordinate, and this function, we'll call it just an fx. And we need to define the intervals. So the intervals, for instance, might be one here a and another one here b, and this interval between here and here. So the definite integral is the area of that integral. So say that's a, b, and fx dx. So you can see that the area under the curve between a and b is known as the definite integral. So let me show you how I would calculate the area from 1 to 3 of this function, and let's pretend that this function is x squared plus 2 dx, and that this is 1 and this is the value 3 in here. Okay, we're going to integrate this normally as we would do, and so we'll write equals x squared will become x cubed over 3, and 2 will become 2x. Now we will write a square brackets on both sides, and we will write down those intervals 1 to 3 on the right hand side of the square bracket. And what this means is that we're going to substitute the upper value 3 into this equation, and then we're going to substitute the lower value 1 into that equation. From above, you can see that a, b, we're substituting b and then taking away with the value a. So in blue, I've just substituted 3, and now I'm going to substitute 3 by multiplying it by the 2 by 3. Now it's important that you're going to put now round brackets. Before, notice that we had square brackets. I don't know whether I mentioned, but that's important, the square brackets. Now we're going to take away, and we're going to do the same thing, but with substituting the 1. So this will just become 1 cubed divided by 3 plus 2 times 1, and finish off with a bracket. The next step is just calculating all this. Whichever way you do it, 3 cubed over 3 is just going to be 9, and then 2 times 3 is 6. So that's the first part, and take away 1 on 3 plus 2, and work once more to the next. 15, take 2 1/3, and we'll end up getting 12 2/3. And as promised before, you have a numerical number, and there is no integration constant c. Now there are some really obvious properties of this. For instance, if I added another interval here and I called it c, and I wanted to find the area of this particular interval here, which will make it blue, I'll call this the area A. I'll call the area A1, and I'll call this area A2. Then it's very obvious, therefore, that the integral of AB plus of fx, that same function, and if I add the next area, the second area, which I will call now from B to C of that same function, fx dx, that together should give me the same as the area of A to C of fx dx. So this should not be a surprise that this is one of the properties. One other property that I will mention here is that if I have the integral of A to B of fx dx, then if I was to switch the boundaries where I'd become the lower boundary A, the lower boundary B, and the upper boundary A of fx, what is the relationship between them? One is the negative of the other. And this is another property of definite integrals. I'll give you more examples of these properties, using the properties, in my next video.